Imagine hundreds of discrete, microscopic entities wandering blindly through an empty void. For a long time, their movement is pure noise. Then, crossing invisible local thresholds, they abruptly lock into place, stacking into dense, structured nodes. These dynamics drive the version 0.2 freeze of a minimal stigmergic agent field simulator. Researchers use this strictly restricted environment as a mathematical baseline, a tool to test how complex spatial patterns emerge from the simplest possible rules. The simulation runs on a two-dimensional grid mapped onto a torus, meaning the edges loop back to create an infinite surface. Across this grid lies a scalar field, a mathematical environment that continuously decays and diffuses outward over time. Agents operating on this grid follow local logic. They walk randomly, checking the field concentration in their immediate cell at each step. If that local field exceeds their activation threshold, the agent deposits a discrete packet of mass, represented by the variable delta F, into the environment. The most critical feature of this model is what the agents cannot do. They possess absolutely no advective chemotaxis. They cannot sense a gradient from far away, and they do not purposefully walk toward higher concentrations of the field. Because the agents are entirely blind to the broader environment, any clustering we observe cannot be attributed to active hunting or gathering. The spatial organization is a mathematical null, the result of passive agents trapped by their environment. Without the ability to follow gradients, these agents simply wander aimlessly. They bounce around the grid in a random walk until they happen to stumble across a local site where the field concentration is already high. This creates a dynamic called absorptive trapping. When a random walker crosses into one of these threshold active zones, the high field triggers a deposit event that anchors the agent, effectively capturing it in a sticky region that refuses to let them leave. Once captured, these stationary agents act as persistent sources. They continuously pump new mass into the grid. This builds the local field higher, expanding the sticky zone outward, which in turn traps more wandering agents in a reinforcing loop. To start this loop from a completely empty, dead grid, the model relies on a tiny, spontaneous nucleation probability. This acts as a mathematical spark, allowing a random agent to drop the very first bit of mass and initiate the trapping sequence. This mechanism shifts the logic of spatial organization. Clustering becomes a passive consequence of environmental geometry, a system where simple capture replaces the need for active pursuit. To understand how large these clusters can grow, we have to look at the global math governing the field. The diffusion stencil operates under strict, mass-conserving periodic boundary conditions. Nothing leaks out. This yields a precise mass budget. The total field mass at the next time step is exactly equal to the current mass, minus a decay rate, plus the new deposits dropped by the trapped agents. Because the periodic boundary conserves mass perfectly, the field cannot invent its own growth. It has no independent dynamical autonomy. Every unit of field mass must be accounted for by an agent's decision to deposit. This graph plots the fraction of agents triggered over 2,000 time steps. Focus on the sharp upward curves, where a large portion of the population becomes active. If the field relies on agents, total mass should track this line exactly. Now look at this second chart, mapping the ratio of total field mass against its theoretical ceiling. The curves mirror each other. At a quasi-steady balance, the field mass ratio visually and mathematically locks to the fraction of triggered agents. The scalar field is merely a shadow. Its overall mass is heavily constrained, strictly slaved to the supply of captured agents on the board. So what determines whether the system actually catches fire or remains an empty grid? That relies on a single dial in the model, post-deposit mobility, designated by the variable Q. Let's bring back the triggered fraction graph. Look at the top line where Q equals 0. The agents stick in place, reliably igniting the field. Now contrast that with the flat line at the bottom, where Q equals 1. The field fails to grow. The outcome gets complicated in the marginal states, like when Q is set to 0.10. Here, agents stick some of the time and move some of the time. The transition out of the dead state isn't a clean binary switch. It becomes highly noisy, with a wildly unpredictable onset. This exposes a frequent trap. If a marginal run remains flat by the cutoff, it's often logged as a failure. But these runs must be treated as right-censored data. They simply haven't ignited within the observation window. The emergence of structure in these systems is a stochastic ignition time problem. To map the boundary of spatial order accurately, we must measure exactly when a cluster catches fire, rather than relying on a ticking clock. Before extracting broad conclusions from a spatial simulator, the code itself has to be rigorously audited. Small procedural artifacts easily masquerade as complex natural behavior. This chart shows the top 1% occupancy mass of the grid across different agent densities. The blue line represents the observed clustering, but notice how tightly it hugs the orange line, which represents a perfectly random placement. Measuring raw concentration makes low-density systems look clustered, but that's an illusion. Random chance alone dictates that a few cells will hold most of the agents. True self-organization requires applying an excess over null correction to subtract the spaceline math. Look at this plot of triggered fraction. The red curve traces an asynchronous update rule, where agents calculate moves individually. An early deposit instantly raises the local field for the next agent in the same tick. This reinforcement artificially inflates the capture rate. To prevent this false feedback loop, the version 0.2 baseline strictly mandates two-phase updating. The field is frozen in phase 1, and all agents make their decisions based on that static map before any deposits are processed in phase 2. Without neutralizing random placement baselines and eliminating asynchronous processing, researchers will inevitably document coding glitches and call them breakthroughs. Once we clear away the artifacts and account for the stochastic delays, we arrive at the final evaluation of the minimal model's ignited state as it pushes past the observation window. The model operates exactly as designed, but it lacks a critical mechanism, intrinsic self-arrest. Once the absorptive trapping ignites, the active zone simply grows, devouring the entire screen until it maxes out the available agent budget. Because the growth is completely unbounded, taking a snapshot at time step 2000 and measuring the component sizes gives us a false metric. It tells us how long the simulation has been running, but it does not represent a stable attractor scale. The version 0.2 minimal model definitively proves that excitable absorptive trapping works. However, it conclusively fails to generate finite spatial wavelength selection. The clusters start, but they do not know how to stop. This failure to self-arrest is precisely why this architecture serves as the ultimate null baseline. We now have a perfectly quantified blank slate. The next phase of experimental modeling introduces a refractory resource, variable R, designed to break this runaway outcome. To prove it works, variable R must accomplish two strict tasks. It must actively convert unbounded growth into arrested dynamics, and it must forcefully release trapped agents back into the free pool, ensuring the system doesn't just permanently freeze. The goal is a system that grows and then naturally plateaus. We want to see distinct breathing boundaries and stable internal cycling that sustains finite scale structures, independent of the grid's artificial limits. Initiating growth is only half the equation. True spatial complexity requires a mechanism rigorous enough to dictate exactly when to stop.